Hey guys, Mr. McKinney here, just doing a quick review of our Unit 7. So we started with the fundamental theorem of calculus, and there's two pieces to the fundamental theorem of calculus. The evaluation piece, which has to do with finding the area underneath finding the area underneath a curve, which is the same thing as the value of a definite integral. So how we can use the indefinite integral or the antiderivative to help us find the value of a definite integral. And then we talk about how derivatives and integrals undo each other. That's the anti-differentiation piece. So the first part of the fundamental theorem of calculus says that you can find the area underneath a curve by using the antiderivative equation. So whatever capital F is, if you took the derivative, you would get little f of x. So little f is the derivative of capital F. Capital F is the antiderivative of little f. And if you want to find the area underneath a curve, you can just use the antiderivative equation and plug in your upper limit and your lower limit. So let's look at what this would look like in practice. So if I want to do the integral from 1 to 3 of x cubed plus 1, it's asking what is the area underneath that curve between 1 and 3. So we could use a Riemann sum to estimate it, but if we want the exact value, we can use FTC. So take the antiderivative, x to the 4th over 4 plus x, and now we're not integrating anymore, now we're evaluating it. So we're just going to plug in 3 to both of them, and then plug in 1 to both of them. So we'd have 3 to the 4th over 4 plus 3. Minus 1 to the 4th over 4 plus 1. And then if you simplify that all the way, that will be the area underneath this curve. So the fundamental theorem of calculus says you can use the antiderivative and plug in your upper and lower limit to find the area underneath the curve. Remember that if you had a problem like this, there is no quotient rule for integrals, so you would have to split it up as the integral from 1 to 4 of 1 over root x dx plus the integral from 1 to 4 of negative root x over root x dx. Simplify each of them first. So this one would turn into x to the negative 1/2 dx, and this one would turn into just 1 dx, or just the integral of dx. And then if you want to see the worked out version, you can go back and watch the other videos. But remember, there is no quotient rule with integrals. The other piece of the fundamental theorem of calculus basically just says that derivatives and integrals undo each other. Now there's a couple of pieces that you're looking for. So the number on the bottom needs to be a constant. The variable that is on top should match the variable that you're taking the derivative with respect to. And the variable of integration needs to match the variable that's inside. If those three things are all true, then all you have to do is plug in the variable that's on top. So instead of f of t, the derivative of the integral of f of t dt is just f of x. So it's the same function, you just swap in a different variable. So we have a constant. If I'm trying to find f prime of x is just the derivative with respect to x. I have a constant on the bottom, I have x on top, so this variable matches. 3t squared plus 1 dt, this variable matches. So all I have to do is plug in x, and I'm done. 3x squared plus 1. That's it. Derivatives and integrals undo each other. That's the other piece of the fundamental theorem of calculus. If you don't have just x on the top, if you had, for example, g of x on top, if you had a function in terms of x, you got to remember to do the chain rule. And you can always do the chain rule. The derivative of x is 1, so we're just multiplying by 1. If you actually have a function up there, like let's say we had x to the 4th up here, you would plug in x to the 4th, and then you would have to multiply by 4x cubed. So just remember to do the chain rule if you have more than just x at the top. So for example, the derivative of the integral of the square root of t plus 4 dt, going from 2 to sine of x, let's check all the pieces. This variable matches. We have a constant. and this variable matches. So now I can just take sine of x, plug it into t, so the square root of sine of x plus 4, and then multiply this whole thing times the derivative of sine x, which is cosine x. So if you have a g of x function at the top, if it's more than just x, multiply by the derivative. Or just remember that you always have to multiply by the derivative of the top, and if it's just x, you're just multiplying by 1. If they're both variables, then you're going to have to split it up. So for example, this one, you'd say it's the derivative from 2x to 0 of 3t dt plus the derivative with respect to x going from 0 to x squared of 3t dt. Now there's a little bit more work to do, but we've already covered that in the other videos. Basically, you have to pull a negative out and flip this one and make sure you use the chain rule on this one. Okay, the next concept was Usubstitution, which basically says if your original integral does not match one of our formulas that's on the cheat sheet, then you have to use substitution or Usubstitution to make it look like one of the integral formulas that we do have. So for example, on this problem, I need to figure out what function I should use as my u function so that I can rewrite this integral in terms of u and make it match one of the formulas. And almost always, you're going to be using this formula. The integral of a x to the n dx is a x to the n plus 1 over n plus 1 plus c. The majority of problems can be written as a power equation. Now there are a couple other integrals. We need to know the integral of du over u. We need to know the integral of e to the u du and the trig formulas. But this is the main one that pops up in the majority of problems. Now, it's not always obvious what to make your u function be. Usually you want to try with what is on the inside of parentheses or the inside of a root or the inside of the function if there's a sine or cosine or something like that. So let's just see what happens if I make my u be 5 plus 2x cubed. My du would be 6x squared dx. I have x squared and I have dx. I don't have a factor of 6 yet, but I can get that in there. So this looks pretty good. If I had tried something else, if I had said, okay, well, let's make u be x squared, then du would be 2x dx. And then I would have this square root, and it would get really complicated, and it wouldn't work. So don't want to use x squared. I want to use 5 plus 2x cubed. But sometimes you just have to use trial and error with different u values to see which one ends up working. So underneath here is what I'm calling u. To get my du, I didn't need just x squared and dx. I also needed 6. So I'd multiply the inside by 6 and the outside by 1/6. You can also solve this equation for dx and get du over 6x squared. If you plug in du over 6x squared here, the x squareds would cancel, and you would be left with a 6 on the bottom, which would move out and become that 1/6. So either way, you don't have to do it both ways. This is the way that MathXL teaches it. This is the way that I taught it, where you just figure out what numbers multiply to be 1, put one of them on the inside, the other one on the outside. And it's always just going to be the reciprocal. So we'd get 1/6 integral this 6x squared plus the dx. 6x squared dx together is du. And then this was the square root of u. So 1/6 integral of u to the 1/2 du. 1/6 times, now I can actually take the integral and then add c, since it's an indefinite integral. Now, if it's an indefinite integral, you have to plug your u function back in. So my final answer would be something like 1/6. Instead of dividing by 3/2, I can multiply by 2/3. And then instead of u to the 3/2, I would say that it's 5 plus 2x cubed to the 3/2 plus c. And then I would simplify this. If it is a definite integral, then your start is going to be the same. The way you start the problem is the same, but you don't ever have to go back to the original variable because you can convert the limits from x into u, or whatever variable you're going to use. So for example, on this one, I'm going to use u equals x squared plus 9. So du would be 2x dx. I have an x and a dx, so I need a 2, which means I need a 1/2 out front. Now, since it's a definite integral, I want to figure out what u of -4 is and what u of 0 is. So if I plug in -4, 16 plus 9 is 25. If I plug in 0, I get 9. So this whole problem is going to switch from x's into u's. And then I'll never have to go back. As long as it's a definite integral, you can switch everything into the new variable and then never go back. So instead of going from -4 to 0, I'm going from 25 to 9. 2x dx is just du over the square root of u. This is not an ln problem, even though it's got du over something. It's not ln because it has to be du over just u. So I would rewrite this problem as a power, so u to the -1/2 du. So when I take the integral of u to the -1/2, I've still got this 1/2 out front, and then it's going to become u to the +1/2 over 1/2, going from 25 to 9. Now, like I was saying, since this is a definite integral, since it has limits, as long as you convert the limits into the new variable, you never have to go back to the old variable. So now I can just plug 9 and 25 in. Now, dividing by 1/2 here is the same as multiplying by 2. So if I move that 2 up, those would end up canceling each other out. So we'd basically just have like 9 to the 1/2 minus 25 to the 1/2, or square root of 9 minus, square root of 25, which would be 3 minus 5, which is -2. So again, if it's a definite integral, convert your limits into the new variable, and then you never have to go back. Because the area underneath this curve between -4 and 0 is the same as the area underneath this curve between 25 and 9. And you can graph both of these in Desmos if you want to get an idea or if you want to verify that that's true. So you never have to go back, and you don't need a plus c for a definite integral. All right, the next topic we covered in Unit 7 was differential equations and slope fields. So I'll pick up there in our next review video. Hope this is helpful.